Okay, we are now doing an analysis of the ball rolling down the slope. So let me draw that. So we have a slope of angle theta, and the ball is rolling down the slope, right? The ball will roll down a distance of d, right? In our case, it's 95 centimeters. The angle of the slope is theta. The weight of the ball acts through its center of gravity, center of mass, and we say that the ball is rolling with an angular speed of omega. Okay. Okay. If you look closely using elementary geometry, you will see that if this dotted line is the normal to the slope, then this angle will be also theta, the same angle as the slopes incline. Okay, now we consider the rolling motion of the ball, right? So let's zoom in to the ball itself, right? And let's see it close up. Right, the ball is rolling. Okay, sorry, the ball is rolling. Let's say, to keep things simple, let's consider that the ball is rolling on a flat surface. Right. If you think about it, this point P, the point of contact between the ball and the ground, is actually the pivot for the motion, right? So actually the whole ball at this instant in time is actually rotating about point P. Okay. Okay. Now let us assume that the ball's center of mass, O, is moving with a certain speed, V. Okay. From P's point of view, point O is moving to the left with speed V. However, if you were to position yourself at O and look at P, from your point of view, point P will be moving to the right with speed V, right? So they have the same speed from their own point of view. Okay. The speed of P relative to O is given by circular motion formula, right? So if you are stationed at O here, right, from your point of view, P will be moving to the right with a speed V, and this speed V will be given by R times omega, right, where R is the radius of the circle. Okay, right, this is a common circular motion formula, right? So this is the point of view of O, right? So if you go back to the picture and look at the point of view, look at O from P, you will come to the same conclusion, because P is now the pivot and O is actually moving about P, right? So it is still, and the distance of O from P is R, right? And so the speed of O, right? And since we just now concluded that the linear speed of O and P, right, from each other's point of view is the same, right? So we conclude that this V will also be equals to R omega. Okay, since these two V's are the same, right? Hence, the conclusion is that the angular speed of the ball about P is also omega. So we have concluded that the angular speed omega of the ball about its center of mass, right, omega, is the same as the angular speed of the ball about the pivot P, right? What this means is that any acceleration of the ball about the point P will change the angular speed of the ball in the same way, right? So if anything were to cause the angular speed of the ball to increase about point P, the rolling angular speed of the ball about point O will increase in the same way. In other words, the two angular accelerations are the same. Now we go back to the ball on the slope and zoom in on this the section containing the ball, right? So let's zoom in. Okay, so let's draw a big picture of the ball. Now resting on the slope. Right? Of course the slope again is theta. Right? The weight of the ball of course acts through its center of mass. Right? And again, if you draw the dotted line normal to the slope, this angle will be theta. And this distance will be r, the radius of the ball. And again, the ball is rolling with speed omega. Right. So if we consider this point P, the point of contact between the ball and the slope, what is the effect of this force acting on the ball? Obviously, common sense will tell you that this ball will start to roll anti-clockwise. And not just that, it will roll faster and faster, it will accelerate, right? So what is the torque or moment exerted by this mg, the weight, on the ball, about P, right? So let's work it out. Torque, also known as moment, right, of the weight about P is torque is equals to force times distance. Force is mg, right? That's the force. What's the distance? The distance is the perpendicular distance of the line of action of the force mg about the point. So we are talking about this distance, this perpendicular distance, this horizontal distance. So if you look at this picture, you can see there's a right angle triangle, and this radius is the hypotenuse, and this angle is theta. So we are interested in the horizontal distance, which is r sine theta. So this will be r times r sine theta. So that will be the torque exerted by the weight about the point P, right? And this torque is going to cause the ball to roll faster and faster. Okay, now we consider the effect of this torque on the ball, right? How does it cause the rotational speed of the ball to change? Right. If we are talking about linear motion, we have something called mass, right? So a heavier object, a more massive object, will be harder to accelerate, right? So if you try to push a tennis ball versus a bowling ball, you will find that the bowling ball will be harder to accelerate, right? But now we are not talking about linear motion, we are talking about rotational motion. So in the same way, if you compare, let's say, a plastic football to a heavy bowling ball, you will find that it is much harder to cause the bowling ball to rotate, to speed up rotationally compared to the plastic soccer ball, right? So to quantify this, we have something called moment of inertia. This is similar to mass for linear motion, right? But it's called moment of inertia. Standard symbol is I. Okay, right. So I will not go through the derivation of this moment of inertia for a sphere, but if you look up Wikipedia, you will find that the moment of inertia of a sphere about its center, in other words, if you rotate the sphere about its center, the moment of inertia of the sphere will be 2/5 mass of the sphere times the radius squared. Okay, right? So this is in the case of trying to spin sphere about its center in this way. Okay, in this way, right? Right. So if you are trying to rotate the sphere about its center the diameter passing through its center, then the so-called mass or the rotational mass of the sphere will be 2/5 mass times the radius squared. Right? However, in this case, we are not rotating the mass about the sphere about its center. We are rotating the sphere about point P, which is not the center. Right? So in this case, the axis of rotation is actually here, point P. Right? So we are not actually rotating the sphere about its own center. We are rotating the sphere about point P. Okay? Right? So for this, there's something called the parallel axis theorem. Right? Which tells us that the moment of inertia in this case will be the moment of inertia about its center, which I've renamed I0, plus mass times the distance of the new axis from the center of mass axis. So in this case will be R. So in our case, the parallel axis theorem tells us that the moment of inertia about P will be the same as the moment of inertia about O plus m r squared. Okay, and we know this moment of inertia, so it's 2/5 mr squared plus mr squared, so we get 7/5 mr squared for the moment of inertia of the sphere about point P, about this point. Okay. Okay. At this point, we have figured out the torque acting on the sphere, causing it to rotate about point P, and we have also figured out the moment of inertia of the sphere about point P. Right? So now we know these two facts. Fact number 1 and fact number 2. Right? So now we are going to use this to analyze the motion of the ball. Right. I am sure all of you are familiar with Newton's second law. Right? Which is F equals to ma. Right? That is for linear motion. But in this case, we are talking about rotational motion. So for rotational motion, there is an analogous relationship. Instead of talking about force, which is what is causing acceleration in linear motion, now we have torque, which is what is responsible for causing rotational acceleration, causing things to spin faster. Right? So we can replace the force with the torque. Similarly, in linear motion, we think about mass, the mass of the object, resisting the acceleration. So in rotational motion, we think in terms of the moment of inertia. So we replace the mass with the moment of inertia. And in this case, our acceleration, rotational acceleration is about P, so we use IP. And instead of using A for linear acceleration, we use a symbol called alpha for angular acceleration. Right? So this is the Newton's second law as applied to rotational motion. Okay, now we are almost done. Now we can use the expression we have obtained for torque, mgr sine theta, mgr sine theta, and we can also use the expression we have obtained for moment of inertia, IP, 7/5 mr squared. 7/5 mr squared. And this allows us to proceed. Right? So let's do some simplification. You can see that the mass of the sphere becomes immaterial. It cancels out. Right? We can do some simplification. One of the radius disappears. Right? So we are left with an expression for the acceleration. Alpha to be equals to 5g sine theta over 7r. Yeah, that's correct. Okay, so that is the expression for angular acceleration, which I'm going to call equation 3, right? Okay. Now I'm going to analyze the motion of the ball down the slope, right? The ball travels a linear distance of 95 centimeters in our case down the slope, from the point it starts until the point it reaches the end of the slope. In our case, it is 95 centimeters, right? In our experiment, okay. And if you recall, it took about 4 seconds, right, for total travel time. Right. So how are we? Okay. Let us pretend that a ball, right, rotates through an angle of theta. Right, it rotates through an angle of theta, right? So if the distance measured along the circumference is s, and the radius is r, so by the definition of the angle theta is actually given by s over r. This is how you define angles in radians, right? Okay, so in our case, the total distance traveled by the ball down the slope, the total rolling distance is d, right? Sorry, the total rolling distance is d. So what is the total angle covered, right? So if you go back to this small rotation, if the distance rolled along the circumference is s, then the angle is s over r. So in this case, the total rolling distance, linear distance, is d. So the total angular displacement, right, of the ball, of the sphere, right? Total angular displacement will be in the same fashion as this one. It will be the total circumference distance, which is d, right, divided by r, right? So that would be the total angular distance, so-called, right, covered by the sphere as you wrote down the 95 centimeters of the slope. Okay, right. If you go back to kinematics, I'm sure you are familiar with this formula. S equals to ut plus half at squared. Sorry, at squared. Right? So we can also convert this linear formula into a rotational formula. Right? So instead of linear distance, we talk about the rotational distance. So in our case, it would be delta theta. Right? Up there. We started the ball rolling with 0 speed, whether 0 linear speed or 0 angular speed. Either way, it is 0, right? Half A is for linear acceleration. If you convert to rotational motion, it becomes alpha, which we have on the previous page, and t is of course time. Right. So if we refer to the previous page, right, what did we have for alpha, angular acceleration? 5g angular acceleration is 5g sine theta over 7r. Right? So the distance is d upon r. The alpha from the previous page is, let's take another look, 5g sine theta upon 7r. 5g sine theta upon 7r. Right? Times t squared. Okay? So we can start to substitute in the formula r. But one more thing, simplification, the radius cancels out. That makes it very simple. So you are left with d, which is 95 centimeters, half times 5g, 9.81, times the angle of the slope, sine of the angle of the slope, which is 1.31 degrees, times, upon 7 times t squared. So if you work this out, right, if you take out your calculator and you work this out, you should get, I worked out previously, let me refer. Okay, so if you were to use your calculator and calculate the time taken, you will find that the time taken is 3.44 seconds, theoretically, right? As I was doing the experiment, I collected the time as measured by myself for the ball to roll down the 95 centimeters ranged between 3.7 seconds and 4.2 seconds. So you will find that this actually agrees with our theoretical answer, right? Of course, the measured time is longer due to inaccuracies, experimental errors, such as human reaction time, the ball rubbing against the side walls as it rolls down, thereby slowing it down, or the ball not traveling in a straight line down the slope.